Okay, welcome back. This is the last day. I see some very persistent people here. That's great to be here. I'm honored. So actually, we're going to do, you've seen a lot of estimation of structural models, including dynamic games throughout the week. And I'm going to actually do something that's very, very, very simple. Try to boil this down to the simplest possible problem, a simple static entry game. I'm going to choose that example because it's enough for me to show what I want to show, the implications for all these different estimation methods of multiplicity of equilibria. So that's the topic for today. And so this the talk is really based on a paper by Qilin Su, who's kind of the founding father of MPEC, and he has a very nice paper in quantitative marketing economics that goes through this comparison, and that paper is in the repo. Unfortunately, Qilin's not with us anymore, so you have to do with me. But he makes this very nice, clear comparison. That's very nice. So that's what I'm going to go through. And essentially, we're going to compare like this horse race of different estimation methods, or at least a subset of what he is doing. So a variety of different two-step estimators. And by now we should know that two-step estimators is about you go out and estimate the conditional choice probabilities. Okay, then you estimate that from the data. Given those, you stick them right into the Bellman equation, use the Hartz-Miller inversion to get some predictions of what the values are, the conditional choice probabilities, and then you use that in the sample criterion that you use in estimation. And that can be a variety of different methods, like pseudo maximum likelihood, like what you would use, for example, many of the stuff that Victor has done has been with pseudo maximum likelihood, or method of moments, or minimum chi-squares. So even someone who did at the conference did OLS, right? So that's kind of the guiding theme for most of these two-step estimators. You go out and estimate the CCPs, use the Bellman equations and Bayesian-Nash equilibrium equations to kind of invert the problem, and so we can learn about the structural parameters. Okay. There's also these two-step minimum distance estimators based on equilibrium inequalities. I'm not going to talk about that. That's a mysterious BBL. So I'm not going to talk about it because it's not part of the comparison. But it's a nice paper, worth reading. And then the next, so see, one of the challenges, like Victor alluded to, is it's really actually hard to estimate these conditional choice probabilities, especially when you have like lots of states, lots of players. It's going to be high-dimensional objects, and you only have so much data, right? So how can you do an unparametric estimation of all that? And so that's why at Equilibria and Mira, they would suggest this recursive updating of the conditional choice probabilities using the best response mapping. Now here today, maybe it's a little bit ridiculous because the game you'll see is very, very small. Like there's essentially only one choice probability for each player. There's no states, okay? So it's just, two probabilities, probability of investing and probability of not investing. And they're the same across all the different players. Yeah, anyway.
Could you clear these estimation methods for dynamic games?
Okay. So the idea here is, these are for dynamic games, but we're going to consider a static game today. Okay, and then later today, we're going to look at dynamic games. Okay, and you have to do, two-step least squares. And so Kasahara and Shimatsu, they're doing like a variant of NPL. It turns out to be a little bit unstable. And so they have a way of kind of dampening that estimator. And then this last approach is MPEC, right? Instead of doing the Hartz-Miller inversion and the CCP estimation, they want to do maximum likelihood, right? And so how do you do maximum likelihood? Well, you maximize the likelihood subject to the constraints implied by the model. So that's the Bellman equations and the Bayesian-Nash equilibrium equations that everybody's playing best response. And so they're proposing that because doing maximum likelihood with the nested fixed point algorithm just seems like to be out of touch with reality. It's too hard. And I'll tell you a little bit why. In principle, you need to compute all the equilibria of the model, which is not so hard in this context because it's a static game, but in dynamic games, it could be harder. Anyway, so let's just start with a simple example. There you go. It's so simple. Okay, it's gonna come and go, I guess. Exit entry, right? That's what it's all about, right? Trying to illustrate. Okay, so we got two firms, A and B, okay? And they're gonna just take binary choices. Gonna serve the market, I'm not gonna serve the market. Okay, they're not thinking about the future, okay? So it's just, do I want to be in the market today or don't want to be in the market today? So we're gonna use DA to be an indicator if firm A is choosing to serve the market, and it's 1 if it's serving the market, and then 0 otherwise. Similar for firm B. Okay, so you have these two indicators of actions of the two players. Okay, and so they're going to get some payoffs, and the payoffs is written right here. Okay, so let's take this slowly. Okay, now if you're not in the market, you're going to get not any payoff except from this epsilon. And guess what? It's going to be I at the extreme value, okay? Because then we have like very nice logit formulas in a second, okay? So we're going to try to make this simple. Now, if you are serving in the market, well, then my payoff, well, I get alpha, but my payoff depends on whether the other firm is there, right? So DB, that's the action of the other firm. So if I'm there alone, then DB is 0, and then I get alpha. If I'm in the market together with firm B, well, then I get this sum, which is essentially beta, right? Because then you subtract alpha again. Okay, so you can say alpha, that's like the monopoly profits, and then there's duopoly profits, that's beta, and then all scaled up by X, which is, that could be I don't know, the size of the firm or something like that. Okay, so it's so X here is like common knowledge state variables. In some sense, that will be the control variables you put into your model, into your logit model of trying to explain whether these firms are in the market or not. Okay, so actually, I don't know is that my computer doing this?
On the other side.
Okay. Okay. Yeah. Anyway, let's see. Let's see how far we get. Okay. I remember these slides, so I don't need them, but probably you would need them. Right? Otherwise, they're in the Dropbox or at GitHub. Okay. So that's our common knowledge state variable. So that's observed by all the players. Okay. They know these X's. Oh my God. Yeah. And then we got the epsilons, which are like private information shocks. And these are independent across the two firms and also across the action. So essentially completely independent. And they're going to be observed by each of the firms, not by the opponents. They are private information, and not for us as econometricians. These are like, just like in the case of Hero Soccer. Okay? It's like an unobserved state variable. So that's kind of the model. Okay, now based on this model, given that this is I at the extreme value, we can calculate, first of all, you can calculate what is the expectation about my profits given my beliefs about, this other agent's epsilon. So that's what we have here, right? So if the other firm B is in the market, well, I'm going to get the duopoly profit. That was beta times X, right? If it's not in the market, I'm going to get 1 minus beta. So that's kind of my payoff in that case, right? And then, we want to calculate the probability that I'm in the market. Okay, that's essentially comparing the expected payoffs if I'm in the market with that zero expected payoff of just staying out, right? So this is like the exponential of 0, right? So 1 is the exponential of 0. So then you get these Lecture formulas that kind of describe this best responses. Okay, you see here's a mapping from choice probabilities of firm B to the choice probabilities of firm A. That's like the optimal best response of the anticipated behavior of firm B to my, as a firm A, my predicted behavior. So what is a Bayesian-Nash equilibrium in this case? Well, that's where these two equations hold. The best response, these best response mappings here, they hold for both firms, okay? So you're gonna have one for firm A and one for firm B, and we can kind of, we can rewrite this a little bit, right? You know, doing the massaging of the Lecture formula, but in the end, it's a mapping from choice probabilities of your opponent to your optimal choice probabilities. And of course, all this depends on the parameters. So every time you change parameters, you change these probabilities. Okay, so let's try to just make a simple graph here. Oh, we need parameters, okay, and then we can make a graph. Okay, so we're going to assume that alpha is 5 and beta is -11, okay? X is 1/2 and 0.2. So there's some differences across the two firms here. And we're not even gonna, I mean, this could be, if you had like different observations of different firms over time in a different markets, this would be like a vector of observables we'll try to control for. Yes?
Just to clarify too, the firms like mixed strategies, but we just see a probability choice in the data. So it's like they're gonna realize their epsilon and conditional on.
Yeah. They know what those epsilons are. They're going to be playing they're not going to be playing mixed strategies because they know what the epsilons are. Of course, you know, the equilibrium that we solve for is in terms of probabilities. Okay. And here they are. Okay. So let's take the best response of firm A as a function of the probability of firm B. Let's take the other one. Sure. Then you have PA on the x-axis. Oh my God. Yeah, okay, so you have PA on the x-axis. That's the blue one. Okay, you see the probability of firm B serving the market is kind of declining in the probability of firm 2 being present. Okay, makes sense, right? Because what happens in this market is if both of us are there, we're going to get beta times x, and beta times x -11, which is much worse than 5 times x, right? Which A is 5, right? So you really got to get knocked over by the presence of your opponent. So it's like an anti-coordination game. And so you can flip the axis and draw it from the other side, and then you have the best response of firm A as a function of the probability of firm B, and that's what you see here. So this is essentially another Lecture formula, okay? And what's the equilibrium? Well, that's where they have mutual best responses. And so let's see, where's the equilibrium? You see? Where's the equilibrium? Yeah? Oh, there's 3. Oh my God. Oh wait, we already have like multiplicity of equilibria. They are crossing each other at several points, right? And so then that kind of begs the question, right? If you are estimating with the CCPs and you put those, or if you're estimating with maximum likelihood, and this is part of the equation here, which one are you going to pick for the likelihood? You're going to pick, you know, equilibrium number 1 or equilibrium number 2 or equilibrium number 3. So that's kind of the challenge here. And I think you can see that already in this very simple example. Okay, now you can also, you know, substitute them into each other, and you get like what we call like a second order best response function, and that needs to kind of be a fixed point on this second order best response function. Okay, so here it's a second order best response function for firm A, and then you see there's these 3 different fixed points. Okay, so if you were to think about just solving each of the best response mappings here as doing successive approximations and looking for a fixed point, how would you go, right? You start guessing an equilibrium here, for example, like you say, this is our initial guess. And then, you know, we will converge by successive approximations to this point, right? Okay, so there's an easy algorithm to find that. See, the problem is it depends us very much on where we start. Okay, so you know, it would be natural to start at the data because the data is informative about what equilibrium was actually played in the data. So yeah, maybe the data was up here very close, and then you say, oh, why don't we just try to see, this is very close to the equilibrium, and let's assume that was the one that generated the data. Oh my God, we converge down here. Yes.
Isn't the middle one kind of unstable?
That's unstable. Yeah. Oh, sorry. That's why I was wrong. So it's going to converge to this one. Okay. So you would say, okay, maybe it's not so realistic. We are playing an unstable equilibrium. Okay. So it's all about how our initial guess of the CCPs, are they kind of to the left or to the right of that unstable equilibrium? That'll determine what equilibrium that we converge to. Okay, so what I'm going to do is I'm going to try to solve for all of them because that's what we need for maximum likelihood. I'm going to solve for all these three different equilibria. So we need a little algorithm that does that, and I don't think it's even worth going through, but let me just talk about this by picture. So what I'm going to do is I'm going to start from the left, and then I'm always going to find this equilibrium. And then I'm going to start from the right, and then I will find that one. Okay, now I know there's going to be at least one equilibrium trapped in the middle, and I can use like a bisection algorithm to kind of trap that down. And then from that, I can kind of search to the right or to the left or whatever I found there, if there'll be more equilibria. And then, so there's a surefire way of finding all the solutions to this simple set of equations. Okay, I just want to try to convince you that I can solve for all equilibria here. It's very simple. Okay, so we can do that. So that's what's going on here. Okay, now this was about estimation. We haven't talked about the data yet, right? So I'm going to do Monte Carlo from this very simple Mickey Mouse model. So we're going to take this model as a data generating process, and we're going to simulate essentially the same equilibrium being played 1,000 times. Okay, so now we have 1,000 data points of the pairs of decisions of the two players. Okay, and each of the time they're going to be either in the market or not, depending on the probabilities implied by the solution to the model. Okay, and then we're just going to keep fix these x's. Okay, so we don't worry about control variables, other things that affects the payoffs. It's all about multiplicity of equilibria. I use these essentially to kind of control different types of equilibria that have different properties. Okay, now given these data, we want to see if we can estimate the structural parameters. And we're gonna try to generate data from equilibrium number 1 and 2 and 3, and sometimes like randomly across the different equilibria and multiple markets. We're going to vary that. Okay, so how do you do maximum likelihood? So here's a likelihood function. So this is pretty standard binary choice, maximum likelihood. Okay, you got the indicator for serving the market for player A times the log of the probability that player A is serving the market times plus 1 minus the indicator for serving the market that is not serving the market times log of the probability is not in the market. We do that for both players, both for player 1 or player A and player 2, and then we just average over all of the sampling. Okay, so that's a likelihood. Now, of course, the trick here, the new thing is we need to derive those choice probabilities. Those choice probabilities, well, they're logit formulas, but they also depend on the conditional choice probabilities of the other player. So we need to find the equilibrium. And so here, PA and PB, well, these are the solutions to these Bayesian-Nash equilibrium equations that I just wrote up, right? The mapping from choice probability of your opponent to your own choice probability. So I have to solve both of these. And that's a fixed point, just like I alluded to with this graph. Like this is a solution. This is, in this case, it's PA, right? for a particular value of the parameters. Now, every time you change parameters, this fixed point will move around, and it becomes an implicit function of the structural parameters. Okay, so this is what we kind of emphasize here by saying, okay, PA and PB are these equilibrium choice probabilities for either the two players. It's a function, implicit function of the parameters. And now we're kind of back to the situation we had with Harold Zucker. Like I also emphasized that they were like implicit functions, the expected value functions in the CCPs would be implicit function of the parameters. And so what you do, if you want to do the nested fixed point, well, you maximize the likelihood subject to alpha and beta, and then every time you evaluate the likelihood, you compute that set of equations here. Okay, so that's how you do the nested fixed point algorithm. So you search over alpha and beta to maximize, oh, that's an interesting clicker, okay. There you go. So you search over the structural parameters to maximize this likelihood function we just wrote up, okay? And then there's an inner loop where you solve these spatial Nash equilibrium equations. And so what's the challenge here in the inner loop compared to Harold Zucker? Yeah, it's finding all the equilibria, right? I mean, it's simple here because, I just show you this little example with a simple algorithm to find all of them. But you need to find all the equilibria, okay? So it's all the solution. Harold Zucker has one equilibrium. There's a contraction mapping, okay? So that means the choice probability is just moving continuously as you change those parameters, and they're just implicit functions, smooth implicit functions. So that's what we need to do in the inner loop. You start with a parameter vector, alpha and beta, and then you solve for all these three equilibria potential, or 3 or 5 or 1 equilibria. And how do you choose the equilibria? Well, why don't we check the one that's most in line with the data, right? The one that's closest to what we actually observed, okay? So that's what we're gonna do. We're gonna choose the equilibrium that gives the highest likelihood value. This is what Victor told us like earlier this week, right? There's two parameters. There's both like the structural parameters, and then there's kind of an equilibrium selection parameter. It's like a discrete parameter because there's a finite number of outcomes, okay? So we're gonna do an inner loop or an outer loop where we search over the structural parameters, alpha and beta, and then an inner loop where we calculate all the solutions and then maximize over those equilibria. So that's what's going on here. So K star here, that's kind of the argument that maximizes the equilibrium specific log likelihoods, if you will, such that they are actually solutions to the Bayesian Nash equilibrium equations. And then what enters here in the likelihood are those that are the maximized ones. Okay, maximized over all the equilibria. Let's take a look at that. This is a likelihood function. So we simulated data, 1,000 burns or 1,000 exit entry situations. And then, with the true value of the parameters, that was like 5 for alpha, minus 11 here. So that's its wide one, okay? And then maximum likelihood, well, that's just maximizing that likelihood function, okay? And looks like MLE is pretty close, so we have estimated it. The camera angle kind of makes it look a little bit weird, like it's not the maximum, but trust me, it is, okay? Yes?
When you're simulating, are you specifying equilibrium you're choosing?
Good question, and I forgot to say that. This is written right here. So I'm choosing, when I'm simulating, you need to make a standard that when you consider the data generating process, if you solve the model for the given parameters, you need to select which equilibrium was played in the data. So here I'm just simulating the same equilibrium number 1, 1,000 times, okay? And that gives me data. I calculate the likelihood for all these different values of alpha and beta, I calculate the likelihood, and then that's done by computing all equilibria and taking the most likely one, and then you put that into the likelihood function. That's what I plotted. Okay, so that seems pretty easy, right? We're getting very close to the likelihood value, to the true value with maximum likelihood. Good news. Okay.
This equilibrium that you're choosing is the one that already gives you the maximum likelihood, and then you're doing maximum likelihood of that very value that you should to the simulation. You will have exactly the same value, or it can give you another likelihood.
Oh, sorry. I just got distracted by a little cough. Can you just repeat it again?
So we have three equilibriums, right?
Yeah.
So here you are simulating or doing the Monte Carlo for the first one.
Yes.
That is the one that also gives you the largest likelihood.
Yes.
And then you do MLE, and surprise, surprise, you get that. But if you choose another one, imagine an equilibrium that doesn't give you the largest likelihood, but you still do MLE.
Yeah.
You will get exactly that, or you will get the first one.
That's, we hope that we will be able to recover the equilibrium that was played in the data, okay? So let me just be clear about it, because multiple equilibria appears several places in this enterprise, right? It's in it's a data generating process. There you need to make a stand on what equilibrium was played, and here I choose equilibrium number 1. Now let's go back and take a look at the likelihood function, okay? Now, when I calculate the likelihood function and calculate the solution to these Bayesian-Nash equilibria equations, I might get like 3 different solutions here, okay? Or let's take this one here. This gives me like the pair of choice probabilities. And then if I have generated the data from this first equilibrium, and I observe, firm 1 is never really doing any investment, and firm 2 is doing a lot of investment in the data that are simulated from this equilibrium, it's more likely that I will pick that right equilibrium when I maximize the likelihood function. That's actually the one that gives the highest likelihood across those 3 candidates. Okay? So yeah, I guess the answer to your question is right in principle, but it's hard. Okay? It's hard because, look at this. Okay? Now this is generated from the equilibrium number 2. Right? This is unstable equilibrium. Okay, so maybe it's just a little bit hard to find, right? So what's going on? I'm changing parameters just a little bit, and you get this huge drop in the likelihood. Okay, it's not even continuous. Okay, it's just this continuous jump at this point here, and well, the true value of the parameters is right here. Okay, and I was able to find the maximum. Okay, I had like the full solution. I could always like find all these 3 solutions and maximize the likelihood. So in principle, I could do that. But why do you think it has this weird shape? I mean, by the way, this is not just because it's this unstable equilibrium. Look at this one. This is equilibrium number 3. It has the same thing. So why do you think it's discontinuous? Exactamundo. The number of equilibria is changing, right? As you change parameters, you say, now let's for example lower beta, right? That makes the game a little bit less contestable. Or you could also have lowered alpha. Okay. So that makes equilibria disappear. Let's actually try to see if we can do that. So that's a little code that generates these graphs here, and let's first see if we can even find the code. Oh my God, what is going on? This is the wrong place. I was not having this before. Oh my God. There you go. Okay, it's over here. And we were lucky. It is in the repository, okay? So if I can't find it, you can find it. Okay, here's a model. It just draws all those different graphs here, and we have the parameters set right here at the beginning, and you can kind of play around with that. So why don't we just try to just see if we can replicate those graphs here. I3 run fix. It's called run fix. And then hopefully, yeah, we see what we saw before, and including those best response functions. Now, what do you think? How should we change the parameters now to make that problem here disappear? Yeah.
The type equilibrium in the original picture is stable, but then there is this jump, like in the second one, that is not stable. This means that when we evaluate with the third set of parameters, that equilibrium becomes the unstable one, and so there should be one on the right that is stable or not?
Okay, yes, I think you're right. Okay, so if we are changing parameters here, then this equilibrium here would disappear. Okay. Both of them would disappear. Yeah, and that's why you have two graphs with cliffs, right? That's what happens, right? Once you go in this direction here, let's suppose that we just, make beta increase a little bit. I said decrease, I meant in numerical value, okay? So let's make it numerically smaller beta, for example, or make alpha smaller, okay? So and see how does that move the best response functions around. Let's see. So this is beta being much smaller, right? So let's run it again. Okay. And now you have like a unique equilibrium. Of course, you can move these parameters just slightly, and what you see is that these best response functions, they're moving around, and for a small change in alpha and beta, suddenly it's just going to disappear. Right? So let's go back to the slides. Okay, so this is what I wanted to say. Okay, now you change alpha and beta just a little bit. This curve just jumps below, and then these two equilibria are no longer there. You're still going to take the maximum over all the equilibria that you find, but now this equilibria no longer exists. And so if this data point generated the data, well, you're left with very low investment probabilities for that firm, because the only equilibrium that exists is the equilibrium where firm one is not investing at all. That's a much, much lower likelihood, right? Because the data says the investment probability was 74%. Okay, and now you suddenly jump to some other solution.
Being played in structural parameters a little bit because of the policy change.
Yeah.
Jump down. That's interesting.
Yeah. And so that kind of also returns to what Victor talked about the other day, right? Like, how do you even compute those equilibria and the counterfactual? Which one to choose? I mean, here we have three, right? But this is a simple static game. Theta will show you models with like millions of equilibria. And sometimes these equilibria, they would just be knocked out. You change parameters in the counterfactual. So there's a challenge of even estimating this model with maximum likelihood, because you need to, find the maximum over all these equilibrium-specific likelihoods. And that's very discontinuous. So how do you even find the maximum if you were able to compute it? That's problem number one. But then there's also the challenge of computing counterfactual. And I think my suggestion is, why don't we just compute all equilibria and the counterfactual and see what is the equilibrium set? And then you select on those based on economic grounds, or like these homotopy ideas that he was talking about. Yes, Lars. Yeah, that's right. Then you can have like a mixture of equilibria being played in the data. Then we need to estimate the parameters that govern that mixture distribution. Yeah, yeah. Dan? Yeah, here there's just 3. Yes, and then sometimes there's only 1. Okay, for some sets of parameters. Yeah, you can say if you don't take the max, that's where you get these equilibrium. Yeah, I'll call them like the equilibrium specific likelihood function. So for a given equilibrium selection, there's a likelihood, right? And then there's going to be another likelihood, maybe a more likely equilibrium on top of that. And the upper envelope of all these equilibrium specific likelihoods, that's what the likelihood function is, at least when you're concentrated out that equilibrium selection parameter. Yes.
That's like in physics when you have like stable and unstable equilibria, right? You have like a test you can do on the second derivative of the potential function to see whether an equilibrium is unstable or not.
Yeah, there's something about the spectral radius of the state transition or something. Yeah.
Yeah, we have something like gauge whether an equilibrium is stable or unstable.
Yes. I mean, in context of dynamic games, that would be, help me out here, Frida, but I think it's you take the state transition and then which is like the Jacobian of the,
second best response operator.
Yeah. Yeah.
Which, you can basically calculate whether you have a stable or unstable if you're close to a stable or unstable equilibrium at any point in the computation.
But then those like are stable or unstable in the structural parameters.
Yeah, that's for given vector of structural parameters, you can figure out if an equilibrium is stable this way.
That's a great question.
Yeah.
And so, you would have to define very clearly what kind of stability that you're interested in.
Yeah.
We will talk later today about the stability of the NPL operator, for example.
Okay.
Which inherits stability of the equilibrium that you're trying, which is generating the data, but it also depends on the sample size.
Because what I mentioned about is like, was there multiple equilibrium, right? If we have a perturbation in something other than the structural parameters, then I guess that it's unlikely that we would ever observe that equilibrium in reality, right?
That's right. But you can see, okay, so fair enough. Let's say this equilibrium is never played, right?
Yeah.
Well.
Why is it the maximum likelihood one?
Well, maybe it's this one over here that was played, right? That was very close. You still have the same sort of problems, right? That this pair of equilibria could disappear, even the stable ones. It doesn't help you. Well, I think it's a fair assumption to say, well, we're going to disregard the stable equilibria as the one being selected from the data.
I mean, there's no like, can't, I don't know, make our way through to a state, like through a unique equilibrium by some stability argument.
No, because here in this case, there are 3 equilibria. 2 of them are stable, 1 is unstable, and I guess there's all these topological index theorems saying there's an uneven number of unstable and then an even number of stable, and they're going to be separated by each other. And so you remove the unstable ones, there's still going to be multiple stable ones. Yeah.
Okay, thank you.
Yeah.
So just to be clear, in each iteration of the gradient,
Mm-hmm.
I'm gonna see a set of vector, a set of parameters, and then for this set of parameters, I'm going to evaluate which of these equilibriums is the largest one. But then for every iteration, I can have a different equilibrium. I mean, just
yes, certainly, yes. And so here I'm not really doing any algorithm. I'm just, my algorithm is just, doing a grid search over all the parameters. But you're right to think about that, because how do you maximize that? So suppose we take like Newton-Raphson or something. There's going to be steps that change these parameters, and then in each step, you have a new parameter vector that could be different number of equilibria, and so searching across that is going to be pretty difficult. Right? So finding the max of this upper envelope.
So just
Yeah.
like a following up, because you're just building the research to find the maximum.
Yeah.
Given that we just can actually draw the surface of the maximum likelihood function, but when it comes to like more complicated game, we may have high dimensional issue. Then is there like a systematic way that to ensure we actually will find the global maximum?
That's a very good point. Yeah, it's very hard to find that maximum with any iterative solver like Newton-Raphson or even like Nelda-Mead that doesn't rely on these second order derivatives or rely on the derivatives to maximize this very weird behaved likelihood function. And that problem doesn't get smaller if you have more parameters than 2. Okay, so I think my point here is to show you how challenging this is. Okay, and don't freak out if you have to start many different places.
Do you know like some way, some paper to discuss how to do that in a systematic way? Maybe like more innovation method in game and especially.
You think about global optimizers. No, not really. It's finding a global optimum, promising that, well, you could do, I don't know, simulated annealing or something, but yeah. I have to disappoint you. It's hard. Okay, but it's a good motivation for doing something else. Okay, so let's do it. Let's look at something else. Now we know the problem is really hard, and I think you will also understand why people they then do something completely different. Okay, so now that was just maximum likelihood with the nested fixed point algorithm, and so here is the same problem, but just formulated in terms of these Bayesian-Nash equilibrium equations as a set of constraints. Okay, so now you maximize this likelihood here. Oh, interesting day. Okay, here, notice here now I'm treating this in this likelihood function. I'm treating the probabilities as variables in the problem. Okay, so I cannot just choose any probabilities. There have to be solutions to the model for the different set of parameters. And that's governed by the constraints. Okay? So now you have more variables. You have the structural parameters you want to maximize with respect to, and then also the investment probabilities or the entry probabilities. And the structural parameters only really affect the constraints. Okay? And so you can throw that after a constraint optimization solver. You're going to put an additional set of constraints on, like we want to have these probabilities be between 0 and 1. Okay? You can tell your constraint optimization solver that as well. And that's just a different approach to implement the same thing. Now, in principle, this objective function is no longer discontinuous. I mean, at least not in the P's, right? And this is just smooth functions as well. This will make the likelihood function that imposes the constraint smooth. Okay, so we can implement this. And if we do that, estimate this model 1,000 times. We make some histograms, and the true parameter of alpha is 0.5. It actually nails it. Okay, you could do both MPAC and NFXP. So this is for MPAC and this is for NFXP. They're supposed to be very similar. Okay, so data generated here from equilibrium number 1 and also from equilibrium number 2 and 3 that looks like they were the difficult ones. We can still do it. I'm not saying that it's easy to find that max, but it's also a very simple case. Okay, so first some remarks here. The likelihood function is discontinuous in alpha and beta for the nested fixed point algorithm because you're maxing out over all these equilibria, taking this upper envelope over the different equilibrium selections. The objective function for constraints and constraints for MPEG is smooth in its variables. Doesn't actually make that likelihood function, the actual likelihood function alpha and beta, smooth, okay? It's the same likelihood function. We're implementing the same problem. Yes, Lars. I couldn't hear that.
Add an additional constraint, which is optimize a set of parameters such that there are three.
How would you implement that constraint?
Such that just such.
But then I would need to know what the solution of the model is, wouldn't I?
It's going to be another equation.
Yeah. Yeah, okay.
That's a nested fixed point problem because you have to compute the equilibrium for each guess of
Yeah.
alpha and beta.
No, I still don't. How would you write an equation to control the number of solutions of a different equation?
You take the derivative of the equilibrium equation, it will be zero.
Oh,
It's
so
going to
for
be the
the
singularity in the system equation. Okay. That's going to be the point at which that's going to be the manifold parameter such that there's exactly two equilibria.
so you can
It could be a knife edge case.
yeah, you can find the knife edge cases this
You
way.
can find all of them, but it's going to be a curve in the alpha case. It's not an easy problem.
Okay. Interesting. Yeah, I haven't thought about that. Interesting. Okay, another thing is here, objective function is not differentiable and not even continuous. So how do you do inference here? You know, I talked to Dennis, okay, and he says, well, asymptotically, all these equilibria, they're going to be separated, okay? So asymptotically, there's no problems, okay? He promised me that's the case, okay? But if you look at this likelihood function here, let's just take the one from equilibrium number 3. You change parameter just a little bit, you get this huge drop in this likelihood. It's clear that the confidence interval for that parameter is really going to be cut off in one side, right? At least in a finite sample. And then I know there's probably always in the limit, as the number of observations going to be big enough, it's going to be locally smooth and you would be not close to the kink, right? But in reality, you have to think about how you get your standard errors. And there are some work on that by Ellie Tamer and co-authors. They calculate these level curves of the likelihood functions to generate confidence bands. Okay, so just be a little bit aware, right? Because your standard asymptotic theory, well, maybe it requires a pretty large number of observations for them to apply. Okay, so this is extremely simple, right? We just have two scalars. Okay, now this is much harder in a high-dimensional dynamic game. Okay, so you don't expect it to be easier when Fedor starts to talk about dynamic games. Okay, now let's move on to a case with multiple market and consider some more estimators. So now we have 25 different markets and we're gonna generate data from that. And we're gonna make a little grid here of X, so we have a little bit of variation of X uniformly between 0.12 and 87. You can see the different values of XA and XB here. And when you vary around X, you also vary around the strategic incentives in this model, and there can be more or less equilibrium. Like in the trivial case where X is equal to 0, there's only the I at extreme value shocks left, and that's a pretty unique equilibrium. You know, they're just flipping coins, and then you figure out what is the optimal investment strategy is based on that, right? So that's a unique equilibrium. But then you vary these X's, and then you can have, like, sometimes it's one equilibrium, and then sometimes there are 3, and sometimes it's even 5 equilibria. Okay? So we're going to use the same parameter values, and then for each of these markets, we're going to solve for these Bayesian-Nash equilibrium equations separately at each market. Potentially, we can select different equilibria being played at different markets. And as you saw, there's multiple equilibria in most of these 25 different markets. And then for each of these markets, we just randomly choose to generate 1,000 data points for that market. And that could be, if there's multiplicity of equilibria, we just flip a coin which equilibrium was actually played. Okay, so how do you do that? I lost track of time. So how are we doing? I have 35. Okay, that's great. Okay, so here's the estimation with multiple markets. So we're still going to try to maximize this likelihood. And now let's, this likelihood here is defined over these market-specific likelihoods. Okay, so for a given value of alpha and beta, we're going to solve for the Bayesian-Nash equilibrium equations for all these different markets. And they're going to be, capital N of them, or 25 different markets. So market by market, we solve for all these different equilibria, the different x's. So there's also going to be different Bayesian-Nash equilibria equations that have also different equilibria. And so we solve for all of them. And now the solutions is going to be indexed both by market and then equilibrium, of course. And so they are the solutions to these Bayesian-Nash equilibrium equations. And then what we're going to do at each market is we're going to take the equilibrium in each market that was most likely played in that particular market. Yes?
How does the computational complexity of this compare to Rust's finding the fixed point? It seems like this is pretty bad.
Yes, that's pretty bad. Okay, because now you can say the additional challenge here is that there's more solutions. Okay, so you can see here maybe there's only three solutions, but in games like Fedor will show, there could be like millions of solutions. So in principle, you need to find all the equilibria. If you follow this strategy, Fedor has a better strategy. But you would have to find all the equilibria, and that's just one of the problems, right? Then there's the problems that this is not a continuous function, and how do you even calculate each of these equilibria when they are not contraction mappings? You cannot solve dynamic games using iterative solutions, because that will give you one equilibrium, and how do you find all the other ones? That's kind of open questions for the next lecture. Okay. Anyway, so we're going to find all those equilibria that or these equilibria, choose the equilibria that was the one that was most likely to be played in each of these different markets. Okay. Okay, so, and you can, that's essentially how you would do the nested fixed point, would just do that computation of the likelihood for every trial parameter of the structural parameters. So they're kind of the same, right? With MPAC, well, you're just going to have now a set of constraints. It's going to be all these Bayesian-Nash equilibrium equations holding at each of the different markets. Okay. So again, MPAC does not explicitly solve the Bayesian-Nash equilibrium to find all equilibrium in each market. These constraints, they just have to hold at the solution where you maximize the likelihood. There could be problems with local maxima, though. Okay. Also note that now, if you have more markets, you're going to have more parameters, right? In this, or more variables in this constraint optimization problem, you're going to have more constraints. Okay, and there's going to be one constraint for each market, for each player. And of course, as this is a dynamic game, you can multiply with the number of state variables. Okay. Yes?
Here we have different markets, and for each market we are doing the routine. But this already is some sort of rule out equilibrium compared to the case where like we have there is only one loop where there is a vector to be chosen, a vector of probability to be chosen, right? Because in theory, so to me it's not, I don't know if like it's different to separate market by market rather than doing our decision, like if the problem is additive.
I'm not sure I fully follow, but you don't like the idea that we are selecting different equilibria at different markets, or is it the implementation of it that you think you're asking about? Yeah. Please tell me again. Sorry.
So if I understood correctly, you are doing this optimization market by market as if they were separate.
Yeah.
I was wondering if there is difference if instead we do a joint profit optimization with all market within only one.
Oh yeah, okay, great question. But that would be treating if I understand your question correctly, that would be treating all the markets as they were the same market, right? If you just say, okay, which equilibrium is most likely to be played across all these different markets? I'm going to do it market by market because I want to potentially allow different equilibria to be played at different markets. I don't know if that answers your question. Kind of, okay. Okay. Anyway, if we do this, we can still estimate alpha and beta, and here are the results for NFXP. And sorry for the poor quality of the histogram, okay? But this is a true value, and there's a small distance to out here, right? We should probably have had more Monte Carlos or less spins, okay? Or look better. Looks like we're doing the right thing, right? So here's the true value, and minus 11 plus 11. And if we increase the sample size, it's going to be looking better, and the variance is going to shrink and all that. So we can do it. So here's what happens sometimes with MPEG in multiple markets, is you get these estimates are actually far away from the true solution. And if you look, if you expect, actually these are converged. These are converged results. So this is something where the optimizer says, well, you found the local maximum to the likelihood function, and all the constraints are satisfied to this last digit. So it is actually in equilibrium. Right? So it's hard to know, is this a result of a local maximum, or is it because, I mean, it's not like you can see it didn't found the equilibrium because the constraints are satisfied. Anyway, this is the implied parameter of beta here, and sometimes it actually gets quite far away. So here's the true value is minus 11, and you get also these values that are pretty far away. If you increase the data, the sample size here, and so the way I'm initializing these estimates with actually the CCP estimates. So if I get very, very good estimates to begin with, I get very good estimates of the CCPs. I can get very good starting values for MPEG, right? Because now I put in like the equilibrium choice probabilities, and I can also put in the structural parameters I estimated with MPEG or with the two-step CCP estimators. I kind of put in the results, and then if you do that, you get more data. It's easier to maximize. Okay. But that's not the case here. And I think I said 1,000, but here we have 25 markets only played 50 times. Okay. And so here's the implied difference between the choice probabilities of the true equilibrium, truly selected equilibrium in a given market, and then the one that was implied by the estimation. And there's some variation, and you see here sometimes these investment probabilities are just far off, probably because it just satisfies the constraint at one of those other equilibria that was not played in the data, but was in equilibrium at that set of parameters, and then reported that as a result. So that's a challenge with MPEG. It's really powerful, but sometimes it can run into local maxima. So if you want to do this, you should try to start this at different ways, different starting values. Okay, so there's other ways, right? It's not, there's also the two-step estimators. And now seeing all these problems, you see why this is so popular, right? Because there's nothing about equilibrium selection as solving across all these different equilibria, right? So you just estimate PA and PB directly from the data using, for example, a frequency estimator. Just count how many times firm A invested out of the 1,000 times. That's your CCP, right? Okay, it's simple here because just a scalar, right? So you estimate those, and then there's different sample criterion. So here's one, right, where you just minimize the square difference between the observed CCP and then the one predicted by the best response initialized by the observed CCP. Okay, now, and then you try to essentially minimize that distance with respect to the structural parameters so that this function becomes more and more in line with the observed data. Okay, so two-step estimation involves estimating the CCPs and then minimizing that that distance. Yes.
This first method, do you have to update the p hat every time, or no? You always use the original.
This is just two-step. It's just two-step. Okay, so just estimate p hat once. You throw them into the best response functions. Then you have something you can use. Like you could. This is minimum chi-squared, but you could also do like pseudo maximum likelihood, which is what we're going to do here. So you estimate again the CCPs. Okay, now once you put those CCPs in your best response functions, those logit formulas, right? All the p's on the right-hand side is going to be fixed by the data. And now the whole thing just depends on the structural parameters. It's easy to construct your likelihood. Okay, you just use these formulas here inside of the likelihood, right? So it's these best response functions initialized at the estimated CCPs as a function of the structural parameters that enter into that likelihood function. Okay? So that's what you do. Okay? And here, there's nothing about maximizing over equilibrium. Essentially, what we're assuming is that there was this one equilibrium that was played in the data. That's what we observed. Okay. And so, the issue here is, of course, there might not be any parameters that satisfies this equation. So, maximize the likelihood, right? But if you take if you found the maximum likelihood estimates and put those right in, this Bayesian-Nash equilibrium equation is not going to hold at the estimated CCP. So it doesn't really impose the entire structure of the model, the equilibrium structure. So that's inefficient, right? And you get small sample bias. Anyway, so that's why Victor and Pedro in this paper suggest to iterate. So you start out with estimating the CCPs from the data, okay, and then you do what it just described, right? You do this pseudo maximum likelihood estimator initialized at the initial estimated CCPs, okay? And then what you can do is like a one best replied iteration on the best response function, and then you do it again, okay? Then that gives you like a new set of pseudo maximum likelihood estimates, and then at some point, this might converge, and if we're lucky, it's converging to maximum likelihood. Okay? That's what they did in 2002 paper. Single agent problems works beautifully there. Sometimes it could be a little bit unstable, as you'll see here even in this simple case. Okay, so here are the results for equilibrium number 1 for NPL. Here they are for equilibrium number 2. Let's not worry about that. That's unstable. How can you ever find an unstable equilibrium with doing successive approximations on the best response mapping or this NPL mapping where you have this inner optimization over the structure parameter? That would have to be a contraction. Okay. So that's just against the principle if you have an unstable equilibrium. But even in the stable one, you can kind of converge to a wrong equilibrium. Okay, so I think I'm gonna end with this. I mean, just bear in mind, this example here was also constructed to make NPL fail. I'm trying to illustrate what can go wrong. It's not like I'm saying, don't use NPL. I'm just saying that it can be unstable. The same thing goes with MPAC, right? We are trying to push the limits of these methods to see where they are fragile. The same goes with NFXP, right? You say I'm showing you an example where you need to find all these maxima, find the maximum over all the different equilibria. Maybe there's smarter ways to do that maximization, and Fedor can tell you about one of those. Okay, so I think I'm kind of going to end it with this. Let's see if any questions. Yes.
So among all of these algorithms, what do you think is kind of better in terms of?
Oh, yeah. Okay, this is going to be my personal view. I think two-step estimators, if you have very good data, that's what you're going to do, right? If you have very good data, that means a big sample. You can estimate these conditional choice probabilities very precisely. They provide a very good approximation of the CCPs. And then you're going to be close to something. The additional gain of doing maximum likelihood is going to be smaller, and the additional gains of doing NPL would also be smaller. Right? What? We also talk about another method. It's called efficient pseudo likelihood. Okay, later today. Okay, that's, I think maybe right now that's the best I think it's one of the best things we have for estimation of gains. Yeah.
But we do two-step just for the starting values or for the other algorithms. Step one, do for two steps.
Yeah, do two steps. That's why it's so powerful, right? At least you get some numbers out there as a kind of in line with the data, right? But be careful, right? Because if you are, if you have a model with like thousands of states, and you have many players, and you have, I don't know, 10,000 observations, well, you have to impose some structure on those CCPs, right? Like estimate a very flexible logit that allows for the right interactions. And that's already putting structure in a place where you don't want. You want to put the structure on the structural model. And that's the only place you can get that is by doing maximum likelihood. Yeah, but it's challenging. Anything? Yes?
Something so for two agents, but do these methods apply for the agent, like multiple agents? Or?
Yeah, so let's talk about multiple agents, right? Well, multiple agents, there'll just be one more equation, right? Okay, and these equations here, let's talk about how the model would modify, right? Let's suppose there's another agent here. Now of course, we have to specify how the payoff depends on this third agent is coming in, right? That would appear here, right, in the best response function, right? Because it's appearing in the payoff function how this third agent is acting. So you can say yes, there'll be. You just have to extend this model to have dependence on more players, right? There'll be more variables in this equation. Here would be PA, PB, and here there would be PA and PB, and then there'll probably also be PC, right? And then there'll be three equations. Okay. You can also have multinomial choices. It's not like they enter or not. They could be like, should I invest 1, 2, or 3, or 4? It would be multinomial logit. And then you have to specify how those choices differ in terms of the payoffs across the multinomial choices. Yeah, so of course it could be extended. I just wanted to kind of boil to the simplest possible example. Yeah.
So for these kind of models, if we use MLE, surely we can just apply the standard MLE formula to derive the variance. But I think that thing requires to derive the score and also prediction. Sometimes if the likelihood function is super complicated, then that may not be feasible. Alternatively, we can maybe use bootstrap, but I think if the model becomes super complex, bootstrap will maybe also be problematic. So in practice, what kind of inference method will structural, economists do in the end?
That is a good question, and I'm kind of putting that question out there as a challenge, right? Yeah, because you're exactly right. In principle, we can, as n go to infinity, everything is nice, right? And this, at least locally, the best response or the likelihood function or whatever objective function you use is going to be locally smooth. Yeah? And there's going to be this neighborhood around the true parameter where you can do your quadratic Taylor expansion and all that. It's all going to be nice and smooth. You can use your standard theorems. And there, in that neighborhood, you can calculate both first and second order derivatives. Okay, and then you use the standard methods. But problem is we are probably far from that, or you could potentially be far from the limit, because it's locally is very small. Okay, so it requires a very big sample size. And then doing bootstrapping, well, that's perhaps difficult if it's just hard to estimate the model once. Okay? You might go in and find local optima in some of those cases. Yeah. So are you sure about your bootstrap distribution if you even was able to calculate the right estimates in that case? So that's challenging too. Of course, you're going to start it from the estimate. So probably the bootstrap distribution is going to be easier to get, right? Because you estimate the model first, and then the starting values is going to be where you started. But if you're close to a cliff where this likelihood function drops, well, maybe it can be harder to figure out what's going on. And then the last thing is this essentially making a profile of the likelihood function to calculate these confidence intervals. And there's a method I can't remember on the top of my head. Maybe Fedor, he knows more, but there's these ways of constructing confidence intervals based on level curves on the likelihood by Elliot Tamer and Chernosukov and others. Yeah, we can put the reference in the box. We haven't tried it out ourselves. We just want to say, okay, it's difficult. Yeah. Yes.
When is the static game sufficient? When should we go the complex dynamic way?
Well, when there's dynamic implications of the choices. Yes, but starting with a static game is always a good idea. I mean, to get something working as a clear description of your data. So if any of you want to start doing applied work, starting with the static game is not a bad starting point. And that also holds for the discrete choice models. Maybe you think of the static dynamic model. I don't know if you can say that, but the static representation of the dynamic model as being maybe a reduced form for estimating the conditional choice probabilities. Okay, so it's a discrete choice model, multiple choices, and then a bunch of state variables implied by your dynamic model. Now, if all those state variables doesn't really matter for the choices, they should, right? They should. The conditional choice probabilities are functions of the state variables. If they are not really in your reduced form, very flexible logit model, static logit model, if you don't see that they are important at all, well, no reason to start coding up the Bellman equations, right, with those variables. And that's another really advantage of these CCP methods, is that you can really quickly get to the data and analyze the relationship between the state variables and the observed outcomes in a reduced form way. You just try new variables, put them in, do some more in Stata, I guess, if you like Stata. I don't. How are we doing on time? I think we probably stop, right? So let's one more in the break. Okay, so. Okay. And what time do we start? I forgot.
Yeah, pretty far.
10:45. Okay, so let's take a good break, right? Have a drink when it arrives. Yes, sorry for not, you know, it's